right? If you take this long form of periodic table, we have rows and columns, and here also they try to keep them in a vertical column or in a horizontal column. Right? So the first attempt was made by Dobereiner. So it is also famous as Dobereiner's law of triads. Dobereiner's law of triads. Triad means
set of three.
Triad means set of three elements. According to him, average of extreme elements, that means first and third element, is approximately same as atomic mass of the middle element, right? So if I consider three elements as a set, so let me consider as capital X, capital Y, capital Z, having atomic mass small x, small y, small z. Then, according to Dobereiner, small y is equal to x plus z upon 2. Average atomic mass of extreme elements. Extreme elements means 1 and 3 is equal to atomic mass of middle element. Right. If you consider some example in this way, if you take lithium, sodium, potassium, all these three elements are of having similar property. So lithium atomic mass 7, sodium 23, potassium 19, 39. Right? Now, if you take average, so what do we have to take? 39 plus 7 upon 2. So 39 plus 7 upon 2. What do you get? 46 by 2. 23. So, do that statement satisfied here?
Yes.
So, as such, we have given some examples. Right? But at that time, only limited number of elements are known. So, he placed only few elements in such a triad system, but not successful in explaining or in placing all the elements in such triad systems. So later, another proposal was made by another scientist named de-Chancortois. De-Chancortois helix model. They are also called as telluric helix model. De-Chancortois telluric helix model. Let us assume a cylinder here. I am assuming this as axis of the cylinder, passing through the mid of it, passing through the midpoint of it. Let me consider this as the axis of the cylinder. On the surface of the cylinder, he made 16 vertical lines. On the surface of it, he made 16 vertical lines. right? After that, he had drawn a helix at an angle of 45 degrees. For example, we consider this as axis, right? So, by making an angle of 45 degrees, he plotted a helix. We know that they are alpha helix, beta helix, maybe in clockwise direction or anti-clockwise direction, right? So, let me assume this as an alpha helix, right? At an angle of 45 degrees. Then what to do? This will cut this 16 vertical lines. Totally, how many vertical lines he has plotted? 16 vertical lines. Over the surface of cylinder. Now, when the helix model was drawn, this state is some sort of staircase is generated with certain points which cut the vertical lines. Elements with atomic masses differ by 16 or multiples of 16 fall on same vertical line. And show some similarity in their properties. This is de-Chancortois telluric helix model. Newland's law of octaves. So, he also arranged elements according to their atomic mass. Here also elements are arranged according to their atomic masses. Dobereiner also arranged elements according to their atomic mass. Right? So, also arranged elements according to their atomic masses. And we observed every eighth element show similarity in property with the first one. Every eighth element show similarity in properties with the first one, right? Similar to musical notes. Similar to musical notes. What are they? Do, re, la. So la si. Do re mi fa so la si. And after that again you should get do. Or we may write as again it is nothing but repeat. Sa is the repeater. So at the time whatever the elements are known, try to place them in an order. Okay. So starting from lithium, if I consider it as lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, then you will get sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and then you will get potassium and so on. Right, and so on. So lithium shows a similarity in properties with sodium as such, but this is not successful in explaining all the elements. Maybe different reasons. Atomic masses of all the elements are now known exactly, so there may be some differences in atomic masses. Few elements have not yet discovered to keep them in an order. Maybe several reasons. Right? So there are some exceptions. There I know. Fails in case of manganese, nitrogen, phosphorus. Fails in case of manganese, nitrogen, phosphorus. And also oxygen, sulfur, iron. Fails in case of nitrogen, phosphorus, manganese, oxygen, sulfur, iron. Many elements are placed at wrong positions due to their atomic masses which may not be exact. Many elements are placed at wrong positions due to their wrong atomic masses. This may be the reason. Right? So relatively compared to other models, this is a better one. Right? So successful than other models. Later, another scientist, Lothar-Meyer as well as Mendeleev Russian. Lothar-Meyer is German. So both done few experiments independently and both has proposed another model at the same time. So at that time, let me start our discussion with the Lothar-Meyer curve. Because of its difficulty to remember, they ruled out this, but it was successful one. That means there is no such flaws as the of earlier models. It was a bit successful one, but because of its difficulty, they have ruled it out. So Lothar-Meyer curves, actually Lothar-Meyer plotted a graph between atomic volume and atomic mass. Atomic volume versus atomic mass. So what he observed is some sort of graph similar to that of some peaks like this was observed. Right? Graph with certain peaks are observed. And what he found is, he found elements of alkali metals at the top of the peaks. So let me consider hydrogen, helium, let me take it as lithium, sodium, potassium, rubidium as such. Beryllium, magnesium, calcium, strontium, scandium, titanium, vanadium, chromium, manganese and so on. Fluorine, chlorine, bromine, iodine and so on. Right? Just he placed all the elements, but I am projecting only few elements. Right? So what we observe in this table is alkali metals are at peaks of the curve. Alkaline earth metals, at around middle of descending peaks. Halogens are at around middle of ascending peaks. Transition elements are observed to be placed at the foot of the peaks. So, at the foot of the peaks, they have observed transition elements. Alkali metals are observed at the peaks. Alkaline earth metals are observed at the around middle of the descending peaks. Halogens are observed at around middle of ascending peaks. But this is also ruled out because of its difficulty to remember the position of every element in the graph. Right? So this is also ruled out due to its difficulty in remembering the position of elements. In the graph. Our motto of periodic table is to make it simpler, to make it easy to remember all the elements, and we need to predict their properties based upon the table, right? So because of its difficulty, this Lothar-Meyer curves were also ruled. So according to Lothar-Meyer, elements are placed based upon their physical properties. So till now we have arranged elements based upon their atomic masses, but whereas Lothar-Meyer has proposed this based upon their physical properties. Particularly, he calculated atomic volumes of every element based upon their density and atomic mass. Right. So can I say periodic properties of elements are periodic functions of their atomic volume or physical properties, right? Or we say periodicity is observed based upon physical properties. Till now, periodic properties of elements are periodic functions of their atomic masses. So how atomic volume is calculated? Atomic volume was calculated by using atomic mass upon density. Accordingly, they have calculated. Mendeleev's periodic table. This is the first form of periodic table. Till now, we have not framed a table in some format, right? So at this time, he also proposed this in the year 1869 at the same time. Because of its easiness, right? This table was famous, whereas because of its difficulty, they have ruled out this Lothar-Meyer. But nothing wrong in it. Both have made similar error. Now coming to Mendeleev's table. So approximately 63 elements are known. He is the first one to propose vertical columns and horizontal rows. So place elements in rows and columns, right? Rows means horizontal, huh? Where we call them as periods. Whereas columns, they are vertical, we call them as groups. Right? Place the elements in rows and columns according to their increasing atomic masses. Increasing atomic masses. So according to Mendeleev, periodic properties of elements are periodic functions of the atomic masses. So let's write that. According to Mendeleev, periodic properties of elements are periodic functions of their atomic masses. If I consider as a hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, then sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, below that aluminium. Silicon, arsenic, selenium, bromine, and so on. Right? So boron is nothing but scandium. Aluminium is nothing but gallium. Right? So this is how you place the elements in the periodic table. In addition to that, he placed a few elements of nearly same atomic masses in one last column. Let me call that as 8th column. After this aluminium and so on, he placed the iron, cobalt, nickel, which is having similarity in their atomic masses, nearly same atomic masses. He placed all these three elements of nearly same atomic masses in one group, right? So let me consider this as 1, 2, 3, 4, 5, 6, 7, 8 in 8th group. Right? Iron, cobalt, nickel, osmium, iridium, platinum, ruthenium, rhodium, palladium. So as such he placed the such elements. So what is silicon? Silicon is germanium. Silicon is germanium. So scandium, let me take it as a titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, then aluminium, silicon, and so on. What you will get here now? Arsenic. Here you will get selenium, bromine. After that, rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, and so on, in such form. So the problem in this table is he placed all metals, non-metals, metalloids, all placed in the same column. So he has not separated metals and non-metals. Shall I rub this part? Why these three elements are placed together? Why these three elements as placed as a set in the same 8th column? Because they have nearly same atomic mass. What about these boron, aluminium, silicon? These elements are not known at the time, but he predicted the positions and he left blank at that positions, right? So predicted existence of some elements and left space for them. predicted their properties also. Right? So what are the Eka boron is nothing but scandium, Eka aluminum is gallium, Eka silicon is germanium. Next. At some positions, elements are not placed according to their atomic masses. According to their atomic mass order. But given priority to their properties. At some positions, elements are not placed according to their atomic masses, but given priority to their properties. We call this as anomalous space. What are anomalous space means? In Mendeleev's table, few elements are not placed according to their atomic mass order, but he has given priority to their atomic properties. By giving priority to their properties. Example: iodine, tellurium. Tellurium, iodine. Iodine is having mass number of 127. Tellurium is having mass number of 128. Right? But tellurium was placed before iodine. Right? This is placed before iodine. So where you get this iodine? Where you get tellurium? Tellurium is found in 6th group, whereas iodine is found in 7th group. This was placed in 6th group, whereas iodine in 7th group. This is one anomalous pair. Similarly, argon and potassium. Potassium mass number is 39, argon is 40. Similarly, thorium and proactinium. Thorium, proactinium. This is a 231, this is 232. Just we have arranged them, but later, at the time of Mendeleev, these elements are not known. No inert gases were found, but if after the discovery of inert gases, what they have done, they just placed out the inert gases in this 8th period. Just they placed it. They perfectly fit the position. But when they placed inert gases, inert gas argon is just before potassium, whereas argon mass number is 40, potassium mass number is 39. So that also created another anomalous state. He made some corrections to their atomic masses for few elements. Particularly, yesterday we discussed platinum and gold. Atomic mass of platinum was corrected and was placed before gold. The main drawback of Mendeleev's table is anomalous space, and also isotopes were not placed. Reason: isotopes have same atomic number but differ in their mass number. So if you are arranging elements according to their atomic masses, we need to place isotopes also, but that was not placed. Of course, isotopes were discovered later, right? So if you want to place elements particularly purely according to Mendeleev's table, we need to place isotopes also, but it is not satisfying. Later, Mendeleev made a small modification in the table by introducing A and B subgroups in every group. In this Mendeleev, so the Mendeleev's table has nothing but 7 horizontal rows and 8 vertical columns. 8 vertical columns are nothing but groups, right? So there is no variation or there is no separation of metals and non-metals, right? And also more reactive elements and less reactive elements are placed together. For example, if you take potassium, potassium is highly reactive, copper less reactive. So more reactive and less reactive elements are placed together. But of course, potassium shows +1 state, copper also shows +1 state. So there is some similarity in properties, but there are many dissimilarities also. But he placed them together. So what Mendeleev has done, he introduced A and B subgroups in every group, right? And he separated more reactive and less reactive, and he separated metals and non-metals also. So another drawback in Mendeleev's table is metals, non-metals, metalloids, all are placed together. Let me write as metals and non-metals are placed together. Right? Few elements do not even follow their properties, but they are placed together. So let me stop here regarding Mendeleev's table. So next study was Mendeleev's periodic table, or we also call it as modern periodic table, right? Whereas Mendeleev's table is periodic functions of periodic properties of elements are periodic functions of the atomic numbers, right? So already we discussed that in atomic structure chapter. When we plot a graph between frequency, square root of frequency versus atomic number, you will get a straight line, right? Not starting from the origin, you will get some straight line, right? Making such an angle, or we can say with positive slope, a straight line with a positive slope, right? So based upon that, we have given an equation, root nu is equal to A into z minus b, where z is atomic number, right? So from there, he proposed periodic properties of elements are periodic functions of the atomic numbers. Till now, atomic masses, except Lothar-Meyer, where Lothar-Meyer given a priority to the physical properties. Based upon physical properties, they are that means based upon atomic volumes. So next study, modern periodic law or Mendeleev's periodic table. Let us talk about this.